Very good morning, students.
Good morning.
Good morning, sir.
Good morning, sir.
Good
Good
morning,
morning,
sir.
sir.
Good morning, sir.
Good morning, all of you. So, without wasting any time, let us start with the discussion. Last class we were discussing about coordination compounds and the terminologies. In that, the last point of our discussion is flexidentate ligands, right? So let us share the PPT. Yeah, this was the last point of our discussion. Flexidentate ligands are those ligands which can change their density. We know cobalt in the +3 states form coordination number, complexes of coordination number 6. So in both the cases, coordination number is going to be 6, both the complexes. Yes or no? In both the complexes, coordination number is going to be 6. But if you look at complex 1, there are 5 ammonia molecules where ammonia is acting as a monodentate ligand. So sulfate should now act as a monodentate ligand only. Then only you will be having a coordination number 6. If you look at the second molecule, the cobalt coordination number 6, 4 ammonia are there. So sulfate should act as a bidentate ligand, where the 2 O minus from the 2 oxygens of the SO4 2 minus, they should be forming a coordinate bond with the cobalt. So these are your flexidentate ligands. What are ambidentate ligands, students? Ambidentate ligands.
That have two donating groups, but only one can donate at a time.
Very good. So ligands which have 2 donor atoms, but at a time only one donor atom can donate the electron pair. Write down the list. So Cn minus, Nc minus. So donation can be from carbon sides as well as from the nitrogen side. If it is from the carbon side, we are getting cyanide. Ide you have to replace with ido. So cyanido. If it is from the nitrogen side, we call isocyanides. Ide you have to replace with ido. So isocyanido. OCN, OCN, it can be cyanato hyphen oxygen, isocyanato hyphen nitrogen. That is from the oxygen side also we can have the electron pair donation, or from the nitrogen side also we can have the electron pair donation. SCN, NCS. SCN means from the sulfur side we can have the donation, so thiocyanato. From the nitrogen side also we can have the donation, isothiocyanato. Isothiocyanato. NO2, nitro or nitrito from the nitrogen sides. Yes or no? Nitro you preferentially use, and from the oxygen side, nitrito. Yes or no? So nitro N, nitro O, that can also use. Nitrito N, nitrito O, that can also be used. So these are the different types of ligands which can do which have more than one donor atoms, but at one time only one atom is donating. That is said to be your ambidentate ligands. Okay, at one time one donor atom can donate the electron pair. If at a one time both the donor atoms are donating, then what is it called as?
Bidentate.
Bidentate ligand. Yes or no? If one time at a time both the atoms are donating, then it can be classified as a bidentate ligand instead of your ambidentate ligand. All of you just let me know, students, if you are done with this noting part. So ambidentate ligand, flexidentate ligands, polydentate ligands, tridentate, bidentate, monodentate ligands, and denticity, all these things we have seen. That means the classification of ligands. The classification of ligands we have done based on the charge first. Positively charged ligands, negatively charged ligands, neutral ligands. Then based on the number of donor atoms, monodentate ligand, one donor atom, bidentate, two donor atoms, tridentate, three, polydentate, more than two means polydentate only, and flexidentate and ambidentate. After this, is it noted?
Yes, sir.
Yes, very good. So next classification of ligands. So after the charge, after the number of donating atoms, that is density, then you have to classify ligands as a classical and non-classical ligands. On the basis of electron pair donation and accepting tendency, ligands are classified into classical ligands and non-classical ligands. Generally, what should happen? Ligand is your electron pair donor, Central atom is the electron pair acceptor. Central atom is accepting electrons. Ligand is donating electrons. So from the ligand, electrons were donated to the central atom. Because of this donation, what type of bond is going to be formed? Sigma bond.
Core. Sigma
Yeah,
core.
a coordinate bond is formed that will have sigma character. From the central metal atom also, there are some ligands, students. There are some ligands where they have a tendency to accept electrons. They have a tendency to accept electrons from the metal atom. Central metal atom can be now donating the electrons to the ligand. If I am accepting electrons, what do you mean by that? That means I should have some vacant orbitals. Yes or no? If I am accepting some 10 students into my classroom, there should be some vacancy to accept the 11th student. If there is no vacancy, there is no acception. Acception and attraction, they are different. Listen, understand this carefully. The ligand is accepting electrons from the central atom. That means the ligand should have vacant orbitals. Ligand is a simple atom or a metal ion or a molecules we have generally. Do we have ligands? Simple atoms, fluoride, chlorides are also there. But those ligands which are accepting electrons from the central atom, they are molecules. In an atom, where are electrons present? In atomic orbitals. In a molecule, where are electrons present?
Molecular orbitals.
Molecular orbitals. So the pi star molecular orbitals of the ligand, they are vacant in some of the ligands. Since pi star vacant orbitals are there, the pi star molecular orbitals of the ligand are vacant, they can accept electrons from the central metal. They can accept electrons from the central metal. So this acception cannot lead to the formation of a sigma bond, rather it will be leading to a pi bond formation. That means here what is happening, students? Sigma and pi character. So there are some ligands, write down this. There are some ligands. There are some ligands which can accept, which can donate and accept, donate and also accept electrons to central metal atom. These are called as, and these ligands will form bonds with the central metal atom. CMA stands for central metal atom, which has both sigma and pi character. Whatever the bonds they are going to be formed between the central atom and the ligand, in these case of non-classical ligands, they exhibit both sigma and pi character. Yes or no? Write down this, all of you. All of you note it down and let me know. If you are done, you can just type letter S in the comment section, or you can just say it on mic as well. Aditi says done, very good. Kushi done, very good. Vaishnavi done. Okay, fine, students. Let us proceed then. Kanishka, very good. So let us look at non-classical ligands and classical ligands, both. So those ligands which can only donate lone pair into the vacant orbital of central metal atom through sigma coordinate bond, these are said to be non-classical ligands. What are these? They are actually donating the electron pair to the empty orbitals of metal. That's it. Vacant orbitals of metal are present. They were actually accepting the electrons from the ligands. The back donation is not happening. So the ligands which can only donate lone pairs in the vacant orbitals of central metal atom through sigma coordinate bond, they are said to be classical ligands. Like example, ammonia, water, H2O, fluoride ion F minus, all these are actually donating the electron pairs to the central metal atom, so only form sigma bond. So they are called as classical ligands, right? Non-classical ligands, this is nothing but your synergic bonding as well. Okay, those ligands which can donate a lone pair in the vacant orbital of central metal atom, and at the same time it can accept electrons from the metal species into vacant orbital through pi coordinate bond. They are called as non-classical ligands. These ligands are also called as pi acceptor ligands. Pi acceptor ligands or pi acid ligands. Why they are called as acid ligands? Because they are accepting electron pair. Electron pair acceptor is called as an acid according to which theory of acid bases?
Lewis acid.
Lewis acid base theory says, yes, very good. Lewis acid base theory says whichever accept electron, it is the species which is having a tendency to accept electron, it behaves as a Lewis acid. So the ligand is accepting the electrons also, so that is why it is said to be pi acceptor ligand or pi acid ligands. This is a back donation from metal to ligand, that is said to be synergic bonding. That is said to be synergic bonding. Examples write down all of you. Examples important. CO, carbonyls, metal carbonyls, NO plus, Cn minus, C6H6, C5H5 minus, C2H4, R3P, PF3, trialkyl phosphine, trifluorophosphine PF3 or phosphorus trifluoride. Here we have vacant d orbital in the phosphorus. In all these species, CO, NO plus, Cn minus, C6H6, C5H5 minus, C2H4, we have vacant pi star anti-bonding molecular orbital. Vacant pi star anti-bonding molecular orbital. Prachi, note it down. Simple thing, classical ligands means only a sigma bond is formed. How the ligands are donating the electron pair into the vacant orbital of central metal atom. Right? Done? Non-classical ligands is of utmost interest now. Note down all of you. Note down these examples very carefully. Those ligands which can donate a lone pair into the vacant orbital of central metal atom, and at the same time it can accept electrons from the metal species into the vacant orbital through pi coordinate bond, are called as non-classical ligands. Now you imagine the scenario, students. Metal is there and it is forming a complex with a carbonyl complex. Like we have what? We have carbon triple bond oxygen CO. What is the structure of CO? Lewis dot structure of CO. Carbon will have how many valence electrons? 4 valence electrons. Oxygen will have 1, 2, 3, 4, 5, 6 valence electrons. Now try to draw the Lewis dot structure, all of you. Share 1 electron from carbon and 1 electron from oxygen. If I share 1 electron from carbon and 1 from oxygen, 3 electrons more remain on carbon. 2 are involved in the sharing. So 3 plus 2, it will be 5. So is it satisfying octet? No. So 1 electron from carbon, 1 electron from oxygen, if I share, there is no use because octet I am not getting. Now share 2 electrons from carbon and 2 electrons from oxygen. Oxygen has 6 electrons. 2 are involved in the sharing part. Carbon has 4 electrons. 2 are involved in the sharing part. How many electrons around carbon? 1, 2, 3, 4, 5, 6. 2 only on carbon, 4 in the sharing, 6 electrons on carbon. How many on oxygen? 1, 2, 3, 4. 4 present only on oxygen. 4 more in the bonding. So 6 plus 6 on carbon, 8 on oxygen. Oxygen satisfied octet. Carbon did not satisfy your octet. So now you can say, since a carbon did not satisfy octet, can I share 1 more electron from carbon and 1 more electron from oxygen? If I share 1 more electron from carbon and 1 more electron from oxygen, what is going to happen?
Oxygen will lose octet.
Oxygen will lose octet. So I cannot disturb the octet electronic configuration of oxygen, and I have to make carbon and octet. How I can do so? I can do that by sharing both the electrons from oxygen to the carbon, forming a coordinate bond or not. So carbon will have 2 electrons on itself only. 2 electrons from carbon, 2 electrons from oxygen involved in 2 covalent bonds. 2 more electrons from oxygen, they were also shared in the coordinate covalent bond fashion. So this is nothing but your, like you can remove the dots here. You can keep dots in this and just keep the type of bonds formed. So carbon will have a lone pair. It has two covalent bonds with the oxygen and one coordinate covalent bond with oxygen. So C triple bond O, carbon has a lone pair, oxygen has a lone pair, and we have a coordinate bond from oxygen to carbon. Is that clear, students? This is how the structure of CO looking like. Now try to write the electronic configuration of CO. What is the electronic configuration of CO? Anyone? What is the electronic configuration of CO?
It has 14 electron, so sigma 1s2, sigma star 1s2, pi 2, sigma 2s2, sigma star 2s2, pi 2px. Sir, it will come in n less than 14, right? Where pi is less than sigma.
Carbon and oxygen. How many are there? 6 plus 8.
14 electron.
14 electrons. 14 electrons means what?
N equal to 14. That's why pi is less
Nitrogen,
than
N2 molecule, right?
sigma.
Sigma
Yes, sir.
1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2.
So sigma star 2s2, pi
For,
2px2.
for N2 we have sigma 2pz first or pi 2px and pi 2py.
Pi representing pi.
Pi
Pi
2px
2px.
equal to pi 2py. Then you have sigma 2pz. This is for CO. Is that true or any difference is there?
So this
there's
is
a
wrong.
difference.
What is the difference, Pachi?
Sir, sigma pz it will come first before pi.
Okay, why Aditi?
Sir, because there is energy difference.
For more than 14 electrons, then only you have sigma 2pz first, then only you have pi, no?
So this one is correct.
This one is correct, but this is wrong. Why it is wrong means not because of pi 2px and pi 2py, pi 2px, pi 2py and sigma 2pz. The correct molecular orbital, the correct electronic configuration of CO will be, write down all of you, sigma 1s2 less than sigma star 1s2, then sigma 2s2 less than pi 2px equal to pi 2py less than sigma 2pz less than sigma star 2p 2s2. All of you note it down. So we have seen the electronic configurations of carbon monoxide, which is also called as a carbonyl, and I am saying that CO has the 14 electrons, and out of these 14 electrons, we have seen the exception of sigma star 2s going beyond sigma 2pz. Why? Because how is CO formed? CO is formed by the combination of carbon and oxygen atom. In carbon atom, we have atomic orbitals. In oxygen also, we have atomic orbitals. So what are the atomic orbitals present in carbon? 1s, 2s, 2p. In the 2p, we have 2px, 2py, 2pz. In the oxygen also, we have 1s, 2s, 2p, 2px, 2py, 2pz. But if you look at CO, students, in the CO, you have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma 2pz, sigma star 2pz. But the point here is, if you look at carbon and oxygen, are they same atoms or different atoms? Different atoms. Which is more electronegative atom? Which is more electronegative atom among carbon and oxygen?
Oxygen.
More electronegative. Since oxygen is more electronegative, the 2s of oxygen has much less in energy when compared to 2s of carbon. The 2s of oxygen was not somewhere here. It was practically of much lower energy somewhere here. So whenever 2s of carbon combines with the 2s of oxygen, you have carbon 2s here, we have 2s of oxygen here. When they combine, they will form two molecular orbitals. What are those? sigma 2s and sigma star 2s. The sigma star 2s will be very, very high in energy, even though when compared to pi 2px, pi 2py and sigma 2pz. Why it is so? Why? Because in the oxygen, whatever the 2s we have, the 2s of oxygen is much lower in energy when compared to 2s of carbon. Why? Because oxygen is more electronegative in nature. And why I am saying only with respect to 2s, why not 1s? Because the second shell is the valence shell. In the valence shell, the 2s subshell has much lower in energy for oxygen when compared to carbon. That is why the anti-bonding molecular orbital sigma star 2s, that will be very high in energy. So what is the bond order in CO? Bond order
3.
3. What is the bond order in CO plus?
3.5.
3.5. If you try to write the electronic configuration like this, CO sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px equal to pi 2py less than sigma 2pz, how much it will result in? Number of bonding electrons, count down. 1, 2, 3, 4, that means 8, and you have removed 1 electron from here, 9. Yes or no? For CO plus, if you write the electronic configuration in this manner, you will have 9 bonding electrons, anti-bonding will be 4, 9 minus 4 by 2, how much it is? 5 by 2, that is 2.5. If you try to figure out the bond order in this way, you will have 1, 2, 3, 4, 5, 5 to 10 bonding electrons. Bond order is equals to number of bonding electrons 10. Anti-bonding electrons is 3 plus 1, 2 plus 1, that is 3. 10 minus 3 by 2, 7 by 2 is 3.5. So CO plus, CO, although it is isoelectronic to N2, you cannot say CO and N2 will have same electronic configuration. Because of difference in the energies of sigma star 2s, we have the exception here. Is that point clear or not? Why I am explaining the molecular orbital energy diagrams of CO and CO plus? Why? Because CO is the ligand which is a non-classical ligand, which is actually accepting electrons from the metal. Because it is accepting electrons from the metal, the CO bond energy, that is going to be disturbed, that is going to be affected. How it is affected, we'll look into now. Write down this point. In CO, the sigma star 2s will have much higher energy. Okay, much higher energy, because in CO, sigma star 2s will have much higher energy because the 2s of oxygen, is lower in energy, as it is more electronegative. No one asks a question, sir, if the oxygen is more electronegative, why the 2s of oxygen should be less in energy? Why? Electronegative elements having electrons is stable. Electrons present in the more electronegative element are stable or unstable? They are stable. Less electronegative elements possessing electrons is unstable. Unstable means high energy. Stable means low energy. Okay. So 2s of oxygen is less in energy. Why? Because the oxygen is more electronegative. That is why you have this scenario. Now you look at this, students. Metal is actually forming a bond with the CO. On the carbon, you have a lone pair of electron or not? On the carbon, you have a lone pair of electron. That lone pair of electrons on carbon, they can be donated. Yes or no? On the carbon, you have a lone pair of electron. The lone pair of electrons on carbon, they can be donated to the vacant orbitals of metal. But in the metal also, we have 3D orbitals where we have electrons. Those 3D electrons on the metal, they can be donated to what? After sigma star 2s, we have pi star 2px equal to pi star 2py. After sigma star 2s, we have pi star 2px equal to pi star 2py, which are empty. So into the pi star anti-bonding molecular orbital, the electrons of metal can be donated. Now I'll ask a simple question. When the CO bond strength is going to be high?
When metal carbon bond is unstable or
Weak, yes or no? When metal is a back donation, metal is donating the electrons to carbon. If that back donation is strong, that means metal carbon bond is strong. If metal carbon bond strength increases, when it will increase? When the back donation increases. If the back donation increases, the metal carbon bond strength increases. If the metal carbon bond strength increases, what happened to the bond strength of carbon oxygen? That will automatically decrease. Yes or no? When the back donation of electrons from the metal to the carbon increases, obviously metal carbon bond strength increases. If a metal carbon bond strength increases, then we can say bond strength of a CO will be decreasing. Now we have again a question, sir. How we can say or how we can say where the back donation is high? From the metal to the carbon, back donation increasing means metal carbon bond is strong. That's fine. But when the back donation is going to be high? When the back donation from the metal to carbon is high, can I say when the metal is in negative oxidation stage, then the back donation would be high or not? When the metal has excess electrons, then the back donation would be high or not?
Yes, sir.
Yes or no? So now metal, whatever the metal ion which has a more negative charge or which has more number of electrons, that can easily donate its electrons to the pi star vacant orbitals of carbon in the carbon monoxide, which is said to be a metal carbonyl. As the metal carbon back donation increases, the MC bond strength increases, so CO bond strength decreases. So with respect to bond strength, I can comment on bond length. First, let me know, students, if you are done with this noting part or not. I'll proceed further.
Sir, I had a
Yes, sir.
doubt.
Yes, Nandana, please.
Sir, you said the pi star 2s, it has higher energy because of that reason, right? So why
Sigma
is it
star.
only, yes sir, sigma star, sorry.
Ah.
Sir, why is it only for sigma star 2s, this character?
Yeah, that's what I say. No, 1s and 1s, they are less in energy. Yes or no? 1s of carbon and 1s of oxygen. Why they are less in energy means because they are the electrons in the 1s of carbon and the electrons in the 1s of oxygen, they are attracted more towards the nucleus. The nuclear charge is very high.
Yes, sir.
Yes or no? Because they are quite stable, their energies are less. There is no much energy difference between 1s and 1s. 1s of oxygen is less energy when compared to 1s of carbon, but that energy difference is not high. Why? Because they are the first shell orbitals,
Yes,
1s,
sir.
1s, which are close to the nucleus, so which are more stabilized, less energy. But if you look at 2s and 2s, they are far from the nucleus slightly. Now the energy difference has been varied greatly. Because of that, the sigma 2s and sigma star 2s, they were also different by large energies.
Yes,
Okay?
sir. Yes, sir.
Okay. And this was a most important exception if you consider the molecular orbital theory. Fine, let us proceed then. Yeah, look at the scenario. Yes or no? Filled orbitals of metal. Filled orbitals of CO. Look at the animation, students. Now the electrons are actually donated from CO to form a sigma bond, and the back donation happened from pi bond. Look at the animation, all of you. See, from the CO, the lone pair of electrons on carbon, they have been donated to the metal to form a sigma bond. From the metal, whatever the electrons we have, they are again back donated into the CO to form a pi bond. So CO to metal, electron pair on carbon donated to vacant orbital of metal. Metal to CO, electrons from metal donated to pi star anti-bonding molecular orbital of CO. Yes or no? So metal to CO, electrons from metal donated to pi star anti-bonding molecular orbital of CO. It will lead to the pi character. It will lead to the pi character. It will lead to the sigma character. Now write down metal to ligand. If a back donation is greater, if a back donation is high, metal carbon bond is stronger. So C double bond O, sorry, C triple bond O bond is weakened. Weakened. So if C triple bond O bond is weakened, its bond length is increased or decreased? Its bond length
Increases.
increases. So which of the following complexes will have highest bond length in the carbonyl? Like that, the questions can be asked. You have to look at back donation, then comment on MC bond, and then you have to comment on CO bond strength and obviously bond length. You can now also say metal to ligand back donation is great, back donation is high if metal has more electron density. Metal to ligand back donation is high if metal has more electron density. That means it is in highest, that means that is if it has negative oxidation state. There are some complexes, you don't need to worry. Sir, why are you saying metals are in negative oxidation states? Metals are electropositive, no? So they should have +1, +2, plus. Why are you saying that they are in negative state? There are some complexes where metals are in negative state. If two metal ions are not in negative state, both are in positive charge, like +2, +3, which can easily donate the electron pair, +2, +3.
+2.
True.
+2.
+3 means size is decreased. No, outermost electrons are accepted greatly to the, attracted greatly to the nucleus. +3 means size is decreased, outermost electrons are accepted greatly towards the nucleus. +2 can be easily donated. So like that, you can compare the CO bond strength, CO bond lengths. Write down the students and let me know. I'll proceed. These are very logical points. That's why I'm spending time here. Can we comment on vibrational frequencies of carbon monoxide? Can we comment on vibrational frequencies of carbon monoxide in different complexes? How we can comment, Suman?
Sir, does it
Yes, Prachi.
decrease?
Does it decrease or increase? Why?
Sir, if bond length is increasing.
See,
frequency.
bond. What is a bond? What is a bond? Like HCl bond, if you talk of HCl, hydrogen somewhere here, chlorine somewhere here. Hydrogen, chlorine. What type of energies the molecules possess? The molecules possess translational energies, rotational energies, vibrational energies, and kinetic energies. Many forms of energies are there. That is why from thermodynamics you can say the internal energy of any system can't be figured out. But a system goes from state A to state B, then I can calculate the change in internal energy. But the absolute internal energy of a system can't be figured out. Same thing here. If I have a bond, the atoms, whatever they are involving in the overlapping, they are not static, they are under vibrations. Yes or no? It is like a spring mass system. You can draw that. It is like a M1, one spring, one mass connected to the spring, and the other end of the spring is connected to a different mass M2, like HCl molecule. So spring mass system is continuously under vibration. No, because of that vibration, it is responsible for some corresponding frequency. mu. So for every bond, there is some frequency which is called as vibrational frequency. For every bond, there is some frequency which is called as vibrational frequency. Stronger the bond, stronger will be the vibrational frequency. Simple logic. Stronger the bond, stronger the bond, stronger the vibrational frequency. Stronger the or higher the vibrational frequency, you can say. Higher the vibrational frequency. Vibrational frequency. So wherever you have a strong bond, there you have highest vibrational frequency. So you have to, if they are comparing or asking the question, which of the following complexes has more CO vibrational frequency, or arrange the following complexes in the order of CO vibrational frequencies, then what you have to do? You have to look at the strength of CO bond. If the CO bond is a stronger bond, then its vibrational frequency is high. How to compare the strength of CO bond? CO bond strength is strong, means the metal to carbon bond, that should be weak. Metal to carbon bond, weak means back bonding is weak. So whichever the complex which has poor back bonding, that will have poor MC bond. If it has weaker metal carbon bond, it will have stronger carbon oxygen bond. If the carbon oxygen bond is stronger, its vibrational frequency is higher. Understood now? Like that, you have to compare the vibrational frequencies. Yeah. When the negative charge on central metal atom increases, when negative charge on central metal atom increases, then tendency of central metal atom to donate electron pair increases. Thus, extent of synergic bonding increases. Thus, extent of synergic back bonding increases. When increasing number of electrons in the vacant pi star anti-bonding molecular orbital CO, then what happened to CO bond order? Synergic bonding increase means what? That means more electrons went to, more electrons donated to pi star anti-bonding molecular orbital of CO. More electrons donated to pi star anti-bonding molecular orbitals of CO. If that is the scenario, then what happened to CO bond order? CO bond order will be decreased. Bond strength decreased. Bond length is increased. Because back bonding high, no. Back bonding high means CO bond strength will be decreased, bond order will be decreased, bond strength will be increased. Is that clear, students? Yes or no? All of you should respond.
Yes, sir. Yes, sir.
Same thing, when negative charge increases on central metal atom, then back donation from metal to ligand increases. So double bond character between metal and ligand increases. So MC bond order, metal carbon bond order increases, bond strength increases, bond length decreases. Bond length decreases. Example, try to figure out now. I have given three complexes to you. MCOX whole plus, MCOX whole minus, MCOX whole 0. Three complexes have been given to you. Arrange these three complexes in the vibrational frequencies of CO bond. Arrange the complexes in the increasing order of vibrational frequencies of CO bond. This was the question. What are the complexes given to you? MCOX plus, MCOX whole minus. This is 1, this is 2, this is 3. 1, 2, 3 complexes. Arrange them.
1, 2, 3 in the same order.
1, 2, 3.
Simple solution you can write. So vibrational frequency is directly proportional to bond energy of CO bond energy. That is inversely proportional to bond energy of MC. So bond energy of MC, where it is higher? Inversely proportional to back donation. So wherever the back donation is higher, like here metal is in -1 stage, metal is in 0 stage, metal is in +1 stage, where the back donation is higher from the -1 stage. So if the back donation is higher, what happens? If the back donation is higher,
CO bond strength decreases.
yeah, metal carbon bond strength increases, CO bond strength decreases. CO bond strength decrease means vibrational frequency will be decreasing, no? So which is the increasing order, 3 to 1 or 1 to 3?
3 to 1.
3 to 1, right?
Sir, the explanation could also be that negative charge also increases on the metal.
Yeah, obviously. So vibrational frequency directly proportional to bond energy of CO. Bond energy of CO, it is inversely proportional to bond energy of MC. Bond energy of MC, where it is going to be highest? Wherever we have back donation, yes or no? So back donation, where it is highest?
The last one.
Negative charge of metal, yes or no? So wherever you have negative charge on the metal, CO is a neutral ligand. So 1 into X, one metal is there, oxygen state of metal, let us say X. So 1 into X, X CO are there. So X into 0, that should be equal to -1. So X should be equal to -1. So in MCOX whole minus, metal is in -1 stage. MCOX whole 0, metal is in 0 stage. MCOX whole plus, metal is in +1 stage. Metal in -1 stage, back bonding is higher. Back bonding higher means MC bond is stronger. MC bond stronger means CO bond weaker. CO bond weaker means weakest vibrational frequency. So 3 should be weakest, then 2, then 1. This is the right order. Got it now?
Yes,
Yes,
sir.
sir.
Yes. To try to answer this simple question, strongest CO bond is present in
Second VCO whole 6. Oh, sorry.
Option 2.
CrCO 6.
Option 1.
option 1, right?
CrCO 6.
Strongest CO bond means weakest MC bond. Weakest MC bond means weakest back bonding. Weakest back bonding means highest oxidation state of metal. So obviously this one, right, students? So this is all about your non-classical ligands and synergic bonding, back donation, vibrational frequencies, CO bond strength, CO bond length, MC bond strength, MC bond length. So like that we can understand. Then comes to the next type of ligands known as pi acceptor and pi donor ligands. So we have discussed just yes, please.
Sir, sir, here metal ion in case of synergistic bonding. So
Yeah,
here metal ion will act as a Lewis acid or Lewis base.
metal ion is accepting the electrons as well as it is donating the electrons.
Yeah.
It has both electron acception and electron donation. It is not just electron acception or not just electron donation. Okay.
Okay. So we can't conclude that it is a Lewis acid or base.
We should not say that because it is accepting the electrons as well as
Okay.
donating. No. If it is just accepting electrons, we can say Lewis acid. If it is just donating the electrons, we can say Lewis base. So the metal ions have a tendency to accept electrons as well as donate electrons. But why we are saying the same in ligands? Because generally all ligands are electron donors only. But we call CO as a pi acid ligand. We specially mention pi acid ligand. Why pi acid ligand? Because whenever it is donating the electrons, it is forming a sigma bond. Whenever it is accepting an electron, it is forming a pi bond. So it is also having a tendency to accept. That is why pi acid ligand. Okay. Ligand is also not effectively acting as a Lewis acid or Lewis base. Its name has been just given as pi acid ligand. Why? Because it is accepting electrons from the metal to form a pi bond. Okay.
Okay, sir.
We cannot say whenever acception and donation both are happening, we cannot define like acid and base, right?
All right.
Okay, fine. Pi donor and pi acceptor ligand. Ligands which donate pi, earlier we have seen what type of ligand? CO is what type of ligand, students? CO? Sigma donor and pi
Pi.
acceptor.
Accept.
Very good. It is donating the electron density to form a sigma bond. It is accepting the electron density to form a pi bond. CO is a sigma donor and a pi acceptor. Now we have pi donor and pi acceptors. Pi acceptor means same, like metal, from the metal if you are getting the electrons, it is a pi bond, so pi acceptor. If the electron donated, they were also pi electrons, then it is a pi donor. Look at the scenario. Ligands which can donate pi electron pair to central metal ion and also accept electron pair from central metal ion through synergic bonding. Donation is also happening. The pi electrons, acception is also happening, leading to the pi bond formation. In that case, these ligands are said to be pi donors and pi acceptor ligands. Example is CH2 double bond CH2. What is it called as? What is it called as, students?
Ethene.
Ethylene.
CH2 double bond CH2 is like 2 carbons are there. So root word is eth. Double bond is there, ethene. Yes or no? But before this ethene, we have placed eta 2. What do you mean by this eta 2? Eta 2 indicates 2 pi electrons were actually shared between 2 carbon atoms. Eta 2. Eta 2 means what? The two, whatever we have CH2 double bond CH2, we have a pi bond. That means we have 2 pi electrons. Where are the 2 pi electrons? Are they present in this carbon or this carbon? Or between both the carbons?
The bonds, the pi bonds.
Yeah, the pi bond. In the pi bond, you have 2 pi electrons. Where are the pi electrons?
Between.
In
They are,
between
they are
oxidation.
shared by 2 oxygens, right? They are shared by 2 oxygens. So whenever I am writing a bond now between metal and ethylene, I have to write CH2 double bond CH2 like this, or metal CH2 double bond CH2 like this, or metal CH2 double bond CH2 like this. Which is the correct way?
Third case.
Third one.
Option.
Third one is the correct way. We cannot say first one or second one, because whatever the pi electrons are donated, they were actually shared by 2 carbon atoms. That is why eta 2 ethylene. It is a 2 pi electron donor. How many pi bonds are there? 1 pi bond is there. 1 pi bond means 2 electrons. So what are those electrons? Pi electrons. 2 pi electron donor. Similarly, we have benzene. C6H6 is benzene. In benzene, we have how many bonds? 3 pi bonds. 3 pi bonds means how many electrons? 6 pi electrons. 6 pi electrons, where are they in benzene? Are they present on 1 carbon or all the carbon atoms?
All the carbon
Between
atoms.
All the
They are-
carbon atoms.
All the carbon atoms, they are all in the delocalization, right? So whenever you are writing a bond from the benzene to the metal ion, how should that bond be represented? So you should have a 6-membered ring. Yes or no? From the center of the 6-membered ring only, you have to donate the electrons to the metal, which indicates the 6 pi electrons of the benzene, they are not shared from 1 carbon atom, rather they are shared from the total benzene molecule because of the delocalization present in benzene. So it is a 6 pi electron donor. What about cyclopentadienyl? Here also negative charge is in conjugation with the double bonds or not?
Yes, sir.
We can write negative charge moving into the pi electron density moving away. We can keep a double bond here, double bond here. We can again move the negative charge into the pi electron density moving away. Resonating structures. I can draw the resonating structures. Double bonds here, double bonds here. So negative charge is not present just as a charge. The negative charge indicates 2 electrons which were in delocalization. So in total, how many electrons are there? 6 pi electrons, 2 double bonds, and negative charge includes 2 more electrons. So 6 pi electrons are there. But these 6 pi electrons are shared between how many carbons?
5 electrons.
5 carbons. So eta 5. So that is why eta 5 cyclopentadienyl. Okay. And whenever you have the donation, you are having the donation like this. So cyclopentadienyl. It is donating the electrons from the center to the metal. So that is what you are having the donation. The electron pair donated to the metal from the pi donor ligand is not from a single atom, rather it is from the total molecule. Is that clear, students? Can I proceed further?
Yes, sir.
Yes, sir. Yes.
Very good. Examples write down. Chromium forms a complex Cr eta 6 C6H6 taken twice, which is sandwiched between two chromiums. So what is the structure? So we have chromium here, eta 6, another eta 6. Yes or no? So we have chromium somewhere here. We have benzene ring. We have one more benzene ring. Between, if my two palms are benzene rings, at the center you have a chromium. So from this benzene ring, the electron donation is happening. From where? From center to the metal. From this benzene rings also electron donation is happening. So that is what we can say the chromium. If these two are benzene rings, chromium is present between. So it is like a sandwiched compound. Yes or no? The chromium is actually sandwiched between two benzenes. Same thing happens in the ferrocene. Ferrocene is a complex of cyclopentadienyl ion with iron. So again, two cyclopentadienyl ions. Again, the two cyclopentadienyl ions, they were actually sharing the electron density to iron. And how, what electron density? The pi electron density. And how the compound is looking like? It is a sandwiched compound, and its name is ferrocene. Zeiss salts. So it is a salt like KPtCl3 eta 2 CdH4. What do you mean by this? This means like a platinum is having 3 bonds from 3 chlorines. Whatever the fourth bond, the K plus is a counter ion. This is your coordination sphere. Yes or no? The coordination sphere is something which cannot ionize. So platinum PtCl3 eta 2 C2H4 that cannot ionize. So platinum is coordinated with the 3 chlorines and one pi donor ligand. What is that pi donor ligand? That pi donor ligand is CH2 double bond CH2. Eta 2 C2H4 means eta 2 ethylene. So this is how your Zeiss salt can be formed. This whole will be having negative charge, which has complexion, which has counter ions as K plus ions. So that is how the structure of KPtCl3 eta 2 C2H4 can be done. K plus will be having a electrostatic force of attraction with the PtCl3 C2H4 eta 2 whole minus. This is nothing but your Zeiss salts. All of you note down.
Sir, in these compounds, how do we find the oxidation number of a platinum or iron or something?
In these compounds, how to calculate oxidation number? So C2H4, as well it is neutral or not? C2H4 is a neutral ligand or not?
Yes.
Oh, okay. Yes, sir.
Yes or no? So we are getting K plus and PtCl3 C2H4 whole minus, where C2H4 is neutral. So 1 platinum 1 into X plus 3 chlorines 3 into minus 1 plus 1 eta 2 ethylene. So 1 into 0, that should be equal to minus 1. So X should be equals to 3 minus 1, that should be 2. So platinum is in plus 2 stage. Okay.
Yes, sir. Yeah.
Okay. Next thing, students, calculation of oxidation number, coordination number, and number of chelate rings. Okay. So oxidation number, how to do the calculation, coordination number calculation, number of chelate rings. Number of chelate rings is equals to density minus 1. The formula we have applied earlier as well. Coordination number is equals to total number of coordinate bonds formed by ligands with central metal atom. CMA stands for central metal atom. Total number of coordinate bonds formed by ligands with the central metal atom. Oxidation number is equals to total charge on the central metal atom. Example, try to calculate for this K4 FeCN6, what is the oxygen state of iron? What is the coordination number and what is the number of chelation rings? Try to figure it out. Oxidation number. So you can write down in the comment section like this. Oxidation number first you mention. Oxidation number. Then you can just keep a comma. Then coordination number. Then you can see keep a comma again chelation rings. Chelation rings. What is the oxidation number? What is the oxidation number? We have 4K plus and FeCN6 whole minus 4. So we have one iron. One iron is 1 into X, 6 cyanide, 6 into minus 1, that is equal to minus 4. So X is equal to plus 2. So oxidation number is 2. Coordination number, 6 cyanides are there. All of them are monodentate ligands. Coordination number 6. Number of chelation rings, how many chelation rings? Number of chelation rings. Cyanide will form any chelation ring. Cyanide is a monodentate ligand, no chelation, so 260. So you can just give your answer like this. Oxidation number, coordination number, chelation rings, 2, 6, 0. Right? Got it, students? Oxidation number of iron is 2. Cn minus is a monodentate ligand. So obviously, Cn minus is a monodentate ligand. Obviously, its coordination number is going to be 6. Number of chelation rings, that is equals to 0. Try to solve for different complexes. For this complex, try to figure out oxidation number, coordination number, and chelation rings. CuNH3 taken for SO4. All of you should try to figure out. CuNH3 taken for SO4. Aditi says 240. Oxidation number, like ammonia is a monodentate ligand and neutral. So CuNH3 taken for whole plus 2. So whatever the plus 2 charge we have on the complex, that should be for copper only. So oxidation number of copper is 2. NH3 is a monodentate ligand. So 4 into 1, that is 4. And number of chelation rings is 0. 240, that is the right answer. Very good. Third one, COEN taken thrice Cl3. Ayushi, Sahil, Faizan. All of you have given the right answer. Very good. Try to give for these students. COEN taken 3 Cl3. What is the oxidation number? What is the coordination number? And what is the number of chelation rings? Faizan has given the answer. Check out once, Faizan. Aditi, check out once. Aishi, check out once. Oxidation number, how to calculate oxidation number? We are getting COEN taken thrice, whole plus 3 Cl minus. En is ethylene diamine, which is neutral. So 1 into X plus 3 into 0 is equals to plus 3. So X should be is equal to plus 3. So oxidation number is equals to plus 3. That's true. Coordination number. Ethylene diamine is a bidentate ligand. 3 ethylene diamines are there. Every ethylene diamine will form 2 bonds. So 2 into 3. Because 3 ethylene diamines are there, 2 bonds are formed. So 2 into 3, that is 6 coordinate bonds are formed. So coordination number should be equal to 6. Number of chelation rings. Chelation rings is how much? Ethylene diamine is a bidentate ligand. So 1 ethylene diamine will form 1 ring. Yes or no? Ethylene diamine is a bidentate ligand. So 1 ethylene diamine will form 1 ring. Denticity minus 1. Denticity minus 1. That is equals to 2 minus 1. That is equals to 1 ring. 1 ring is formed by 1 ethylene diamine. This is for 1 ethylene diamine. For 3 ethylene diamines, how many rings are formed? Number of rings is equals to 3 into 1. That is equals to 3. Got it now? So 3, 6, 3. Number of chelatings is equals to 3. Ethylene diamine is a binded ligand, so coordination number is equals to 3. Oxidation number of cobalt is 3, right? All of you have given the right answer. Very good. Okay, number of chelating rings means number of chelating rings in the total complex, not in just a, not with respect to just one ligand. So this density minus 1, it is a formula for just with respect to one ligand, not in the total complex. Try to solve this. Cu diene taken twice SO4. Cu diene taken twice SO4. What is diene? What is diene? Cu diene taken twice, whole plus 2 plus SO4 2 minus. That is how the dissociation will happen. Diene is diethylene triamine. Diene is diethylene triamine. So what is the coordination oxidation number? Oxidation number will be equal to plus 2 directly, because it has diene is a neutral molecule. Cu diene taken twice whole plus 2 means copper should be in the plus 2 state. Coordination number. So we have diethylene triamine is a tridentate ligand. So tridentate ligand will form 3 bonds. 2 such ligands are there. So 2 into 3, that will be 6. And whatever the chelate rings, number of chelate rings, density minus 1. Density is 3 minus 1, that is equal to 2. So 2 rings are formed with respect to one diene. Therefore, this is for one diene. Therefore, for 2 ligands, 2 into 2, that is equals to 4 rings are going to be formed. Right? Can you try this?
Can you show the previous one?
Note down. Chelating rings, 3 minus 1, that is equal to 2 for one diene. For one diethylene triamine, you have 2 rings formed. For 2 ligands, for 2 diethylene triamine, how many ligands are going to be, how many rings are going to be formed? 4 rings.
Done,
Got
sir.
it? Done. Can you do this? EDTA will have oxygen state of what? EDTA total charge. One calcium is there, so one calcium is 1 into X. EDTA is will having a total negative charge of minus 4. So 1 EDTA, so 1 into minus 4, that should be is equal to minus 2. So X should be is equal to plus 2. So calcium is in plus 2 state. What about the coordination number?
6.
Yeah, coordination number is equal to 6 because EDTA hexadentate ligand which will form 6 bonds. What will be the chelation, number of chelating rings? Only 1 EDTA is there. So 1 into density minus 1, 6 minus 1, that will be equal to 5. 2 comma 6 comma 5. All of you note it down, students. Yeah, oxidation number 2, coordination number 6, chelating rings is equals to 5. Done, Prachi?
Yes, sir.
Yes. You take this as homework. Okay, same scenario. You try to solve this. Then the IUPAC nomenclature of complexes comes into picture, students. IUPAC nomenclature of complexes is also very, very important. You have different rules. Rule 1 is naming of cationic part followed by the anionic part. First, you have to name which part? Cationic part. Whether it is a complex cation or a simple cation, first cation should be named, then only anion. Then you have to name first cationic part. You have to name. After naming the cationic part, while you are naming the complex ion, if the cationic part is complex or anionic part is complex, that doesn't matter. While you are naming the complex ion, you have to follow these rules. In the complex ion, which should be named first? In the complex ion, which should be named first? In the complex ion, you have metal and ligand. You have metal and ligand. Ligand should be named first or metal should be named first?
Ligand.
Ligand. Okay. While naming the complex ion, ligand should be named first. And in the naming of ligand, you have to represent number of ligands present. After keeping the number of ligands, you have to keep the name of ligands. And while naming different types of ligands, use alphabetical order. But do not give preference to numeral prefix. Yes or no? You have to look at alphabetical order of that particular ligand. Then finally, name of the central metal atom. Write down the rules. First, name cationic part. Name cationic part. Next, while naming complex ion, name ligands first, and then metal ion, and then metal ion. In ligands, we have to indicate in ligands, we have to indicate what? We have to indicate same number of ligands by using same number of ligands by using prefixes like, we have to use bi for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. Also, ligand should be named in alphabetical order. Ligand should be named in alphabetical order. Alphabetical order. When we have monodentate ligand, then this is true. When we have bidentate ligand or tridentate ligand, like if I have ethylene diamine, in ethylene diamine I already used di. If I have 2 ethylene diamines, can I say diethylene diamine?
No, sir.
In case the ligand already used, the ligand name itself contains di tri tetra, then bis is used for 2, tris is used for 3, tetrakis is used for 4. Like in case if your ligand already has used di tri, like it is possible only in the case of bidentate and tridentate and polydentate ligands. If the di is already used in the ligand name itself, then you have to use bis for 2 such type of ligands, tris for 3 such type of ligands, tetrakis for 4 such type of ligands, right? And while naming the metal ion, if the metal ion is in the anionic part, like if the complex ion is in the anion, in the complex anion, while ending the metal ion, what should you get? You should use 8. Yes or no? First write down this, then we'll proceed. Done or not, students?
Yes, sir.
Yes, Vaidehi, very good. Yeah, this is what I'm talking about. If central metal atom is a part of anionic complex, use suffix 8. Like if central metal atom is a part of anionic complex, that is complex ion is anion now, then use the suffix 8. Example, whenever you have iron in the anionic complex, use ferrate. Au means ORate. Ag means argentate. CO means cobaltate. Write down this. Fe means ferrate, Au means aurate, Ag means argentate, CO means cobaltate. Fe means ferrate, Au means aurate, Ag means argentate, CO means cobaltate. This is used when the complex ion is the anion. Right? Ferrate, aurate, you should end with 8. If central metal atom is part of complex anion, then we should use it. If the central metal atom is part of cationic or neutral complex, no suffix is used. So for Fe, you should use simply iron, Au gold, Ag silver, CO cobalt. If a central metal atom is a part of cationic or neutral complex, then you should not use any suffix. You should simply write iron or gold or silver or cobalt like this. And do we need to mention the number of counter ions present? Like if we have K4 Fe6, do we need to
No,
mention?
sir.
Why?
Yes, sir. Yes, sir.
So do we need to write tetra potassium, then we have to name this complex ion? Yes or no,
No,
Faizan?
sir. Only
No.
only potassium.
Then you said yes or no just now?
I said yes. We have to write K potassium. in
No,
either
then
number.
where you are indicating like K4 is there or K3 is there, how do you know? If you simply write potassium. If I simply write potassium and then name the complex ion, how do I know whether only one potassium is there or two are there or three are there or four are there?
By finding out the overall oxidation state of the coordination sphere.
Very good. We have to indicate the coordination number, oxidation number, right? Whenever you are indicating oxidation number, you automatically mention how many K plus ions are there. Okay? So you don't need to write tetra potassium or tripotassium. You have to first name the complex, first name the cationic part. While naming the complex ion, name the ligands, use suffixes, use prefixes like di, tri, tetra, penta, hexa. Name the ligands in the alphabetical order. After completing the ligands, name the central metal atom. After naming the central metal atom, you indicate the oxidation state in the parenthesis. That indication of oxidation state in the parenthesis automatically says how many counter ions are there. Okay? We have to indicate oxidation states of central metal atom of in parenthesis, in brackets you can say, after naming the central metal atom. This automatically gives the idea regarding number of counter ions present. While naming, we are writing ligand first, then you are naming the central metal atom. While writing the molecular formula, in the molecular formula, first you write the metal atom, then you indicate the ligands. Like K4 Fe6, first you have mentioned the central metal atom, then you have indicated the ligands. But while naming, you write first the name of ligands, then the central metal atom. That means from the name also, we should be in a position to write the ligand or to write the molecular formula of the complex. From the complex, we should be able to give the name. From the name, we should be writing the molecular formula of the complex. So let us proceed further and try to give few examples. If ligands involve di, tri, tetra in their name, then the number of their ligands is indicated by bis, tris, tetrakis. As I have told you earlier, if di, tri, tetra were already present in the name of the ligand, then you cannot use again di, tri, tetra. Rather, you have to use bis, tris. Okay, for two such type of ligands and three such type of ligands. Try to solve this, students. K4 FeCN6. K4 FeCN6 gives 4K plus FeCN6 whole minus 4. What is the cationic part first? Cationic part is K plus. So potassium, first write potassium. FeCN6 whole 4 minus. In the complex ion, what should name? Ligands first. FeCN6, only one type of ligand is there, cyanide. How many such type of ligands are there? 6. So hexa, cyanide. Cyanide has to be replaced with cyanido or cyano. I have told you, ide you have to replace with ido or O. Yes or no? So that's why cyanide has to be replaced with cyanido or cyano. So potassium complex cation named first. Hexacyano. Completed the naming of all ligands present. Then you have to indicate iron. Central metal atom is present in the complex anion or not? It is present in the complex anion. So ferrate, we have to end with 8. If the central metal ion is in the complex anion, we have to end with 8. What is the oxidation state of iron here? 2. Potassium hexacyanoferrate 2. That is the IUPAC name of K4 FeCN6. Got it or not? Potassium hexacyanoferrate 2. Why I have mentioned potassium first? Because it is the cationic part. What is the anionic part? FeCN6 whole minus 4. In the anionic part, what type of ligands are there? Only cyanides. So hexacyano. After writing hexacyano, what do we have? Iron. But iron is in anionic part of the complex. So ferrate 2. You have to indicate 2 as the oxidation state. These 2, oxidation state 2 automatically indicates how many potassiums are present. So that also we have set. Is that clear? Can we solve next example?
Yes, sir.
You try to give the name. CuNH3 taken for SO4.
Tetraamine copper 2 sulfate.
Copper 2 or cuprate 2?
Copper 2.
Copper.
What is the spelling of amine?
AMMINE.
Yeah, those are the points which you have to carefully concentrate. Only one type of ligand, NH3. How many are there? 4. So tetra, AMMINE, tetraamine. Since the metal ion, since the metal is present in the complex cation, so you should not use 8. So copper only, copper 2. And after naming the positively charged cation, then you have to name the anion, that is sulfate. Tetraamine copper 2 sulfate. Right, very good. Name this.
Tris 1,2 ethylene diamine cobalt 3 chloride.
Why you have placed 1, 2?
Because amine is in the position of first and second carbon.
No, ethylene diamine automatically indicates that is NH2, CH2, CH2, NH2. En indicates the name of En is ethylene diamine only. Okay. You don't need to place 1, 2 again. Ethylene diamine. En stands for ethylene diamine. You don't need to indicate the positions of amine groups like 1 and 2. So tris, how many ethylene diamines are there? 3. So tris, first it will dissociate to give CO En taken thrice whole plus 3 Cl minus. So trace ethylene diamine cobalt, because cobalt is in the complex cation. So cobalt 3. Why it is 3? Because its oxidation state is 3. And a chloride. So trace, after keeping trace, we have to indicate with the within brackets. Trace ethylene diamine cobalt 3 chloride. Got it?
Yes, sir.
Yes, try to name this compound. Next one. CO taken twice, NH3 taken twice, H2O taken twice, Cl3.
Diamine diaqua dicarbonyl cobalt 3 chloride.
Very good, Faizan. Okay. So we have CO is a carbonyl, NH3 amine, H2 aqua. First amine you write down AMMINE, AQUA, carbonyl. Of course, carbonyl C comes later when compared to A and A. So AM, AQ, which comes first? M first. Okay, so diamine. Then you have, because two amines are there, diamine, diaqua, dicarbonyl, cobalt. After writing cobalt, you have to indicate 3 because oxidation state of cobalt is 3. Why? H2O, NH3, CO all are neutral ligands. Oxidation state of the total complex ion is equals to oxidation state of cobalt. So cobalt 3 chloride. Very good. All of you got this or not?
Yes, sir.
Yes, sir.
Yes, very good.
Yes, sir.
Try to name this. CO NaCl taken 6, COCl6.
Hexamine cobalt and 6 chloridocobaltate plus 6.
So how the dissociation happens? Yes, please.
Sir, hexamine, cobalt, hexachloro, cobaltate plus 3.
Hexamine cobalt 3 hexa.
Yeah. We have to indicate the oxidation state of both the cobalt. Okay.
Hexaminochromate 3.
Okay, very good. So hexamine cobalt 3, hexachloro cobaltate 3. How you have figured out? So you have to write the dissociation. So CO NH3 taken 6 whole plus 3 plus CO Cl6 whole minus 3. How we have written this, students? Because if you look at CO NH3 taken 6, NH3 is a neutral ligand, so no charge. But COCl6 chloride is -1, so it is having -6 charge. That -6 you have to divide into two parts. So 3 and 3, right? 6 you have to divide into two parts, 3 and 3. For one cationic part, you have to give +3. For the anionic part, you have to give -3. Yes or no? CO NH3 taken 6 whole plus 3 plus COCl6 whole -3. Now we have to name this first cation. So hexamine cobalt only, not cobaltate, because it is in the cationic part. Hexamine cobalt oxidation state you have to mention. People earlier said names without oxidation state of first cobalt. That is wrong. We have to give the oxidation states of both the cobalts. Hexamine cobalt 3, then hexachloro or hexachlorido, cobaltate. Now because metal ion is on the negative ion, cobaltate 3. Got it or not? Right?
Sir, can you tell the dissociation part again?
So dissociation part, write down CO NH3 taken 6, CO Cl6. It dissociates to give cations and anions. CO NH3 taken 6, one is cation. How much charge is there? You don't know as of now. It is some plus X, you say. And CO NH3 taken Y, it again dissociates -X. Because same charge is there, no? Because as a whole, the molecule, as a whole, this complex is neutral. So if it is plus X here, it should be -X here. Because charge should be same. Now look at CO NH3 taken 6. Ammonia is neutral ligand or not, Prachi?
Yes, sir.
Ammonia is neutral ligand. So ammonia is not having any charge. So with respect to ammonia, cobalt should also be neutral. So as a whole, this is neutral. COCl6 you figure out. Chloride is neutral or -1?
-1.
-1. So how many chlorides are there? 6 are there. So 6 into -1 is -6. So the total charge given by ligands is -6. The total charge of the complex ions, like the total charge of the central metal atoms, that should be +6. Then only the charge is going to be neutralized. Are you getting this point or not? The total charge given by ligands is -6. Why? Because we have 6 ammonia, 6 into 0, 0. 6 chlorides, 6 into -1 is -6. So -6 is the total charge given by ligands. So the metal atoms should be having a total charge of +6. Then only as a whole it is neutral. And now dissociation happened. One complex cation, one complex anion. Can I say both these should be equal? +6 -6, they should be equal or not? Then only you should have total complex ion should be total complex should be neutral. And you have to divide 6 units of negative charge. The 6 units of negative charge should be balanced by 2 cobalt atoms. That means here also you should have the complex ion should be in the +3 state. Why it should be in the +3 state? Why it should be in the +3 state?
To
Because you have to
neutralize.
divide 6 by 2. Yes or no? 3 units you will be getting. So you have to get the complex cation in the +3 and complex anion in the -3. So then +3 -3 automatically charge is neutral. If you divide this 6 by 2, you are getting 3. You are given that to complex cation and complex anion. In the complex cation, ammonia is a neutral. So 1 cobalt, 1 into X, 6 ammonia, 6 into 0. That should be equal to +3. So X should be equal to +3. Cobalt is in +3 state here. What about other cobalt? 1 cobalt, so 1 into X. This is NH3 taken 6. This is Cl6, right? Not NH3. COCl6. So 1 into X plus 6 chloride, 6 into -1, that is equal to -3. So X should be equal to +3. So here the cobalt is in +3 state. Here the cobalt is in +3 state. So total oxidation state of cobalt is +6. Total negative charge is -6. Neutralized or not?
Yes, sir.
So in simple words, what you can do is whatever the total negative charge you are getting from the ligands, that you divide by 2. Not the minus sign, just the magnitude. 6 by 2 is 3. You give this 3 to the cation and the same 3 to the anion, like +3 and -3. So that the anions, one anion with +3, one cation with +3, one cation with +3, one anion with -3, they are going to be neutralized. So if you give +3 and make a cation, -3 and make an anion, you can directly calculate the oxidation states of cobalt. You can directly calculate the oxidation states of cobalt, right?
Yes, sir.
Okay, fine. So try to name this then. Fe4, FeCN6 taken 3. Prussian blue, it is Prussian blue in color. Here Fe4, FeCN6 taken 3. How to name this complex? Here the only logic involved here is, students, the iron is acting as a central metal atom and the same iron metal is acting as a counter ion. Then you have to mention the oxidation state of central metal atom iron as well as the oxidation state of iron which is acting as a counter ion. That is the only logic. Earlier in K4 FeCN6, what you have written? K4 FeCN6, potassium hexacyano ferrate 2. You have not mentioned potassium 1, but now you are going to mention that. If you write down the splitting, how the splitting will happen? How the splitting will happen? Like AX BY, how it splits? XAY plus YB X minus. Similarly, Fe4 FeCN6 splits as 4 Fe3 plus 3 FeCN6 whole minus 4. That is, we have Fe plus 3 ion. The counter ion oxidation state is +3. The central metal atom oxidation state, that is +2. In FeCN6 whole minus, the oxidation state of iron is, how much? +2 or not? In Fe plus 3, the oxidation state is +3. So you have to mention like this. First you have to mention the name of cation. So iron 3, because if Fe is in the cationic part, you should use iron only. Iron 3. You have to mention its oxidation state. Why? Because it is also acting as a central metal atom. And after naming cation, you have to name the anion. How? Ligands first. How many ligands are there? 6. Hexacyano. Now iron is in the anionic complex ion. So hexacyano ferrate 2. So iron 3 hexacyanoferrate 2, that is the name of this particular complex ion. Is that clear, students?
Yes, sir.
Yes.
Now I will give similar example to you. Try to solve. Here also, I should name the counter ion or not? I should give the oxidation number of counter ion or not? Fe3,
Yes.
FeCN6 whole taken twice. I have to mention because same iron is acting as central metal atom as well as counter ion. So what is the dissociation looking like? 3 Fe plus 2 plus FeCN6, 2 FeCN6 whole minus 3. What is the oxidation state of this iron? Counter ion? Iron 2. So how the name is now going to be?
Iron 2.
Iron 2
Iron 2 hexacyanoferrate.
Very good. Iron 2 hexacyanoferrate 3, because here iron is in 3 stage. Iron 2 hexacyanoferrate 3, that is the name of this particular complex. So these are different names. I'll be giving few more complexes to you. Take that as example. Okay. Okay, fine, students. Tomorrow we'll complete the rest examples. Whatever the examples I have given to you, try to practice them and try to solve all the DPP questions and exercises.
Sir, the 2 present outside the bracket in efficiency whole twice, it has no role in the naming. Right?
Sorry, which has no role in the naming?
In FeCN6 whole twice, the 2 outside the bracket.
No, it has no role. This is complete dissociation, right? If it dissociates, we have Fe plus 2 ions and FeCN6 whole minus 3 ions. This 3 Fe plus 2, this has no role. This is just for balancing of this total number of charge. Okay.
Yes, sir.
If it is dissociates, we get how many types of ions? That is obtained by this 3 and 2. Like charge is balanced. Charge has to be balanced, right? Okay, fine, students. Try to solve problems, whatever the homework questions I have given. Tomorrow we'll discuss with the next concepts. Fine. Thank you all, everyone. Bye-bye.
Thank you, sir.
Thank you, sir.
Excuse me, sir.
Yes, Farhan.
Sir, I'm having some problem. Actually, my basics are not very clear, like from chemical bonding. So I'm having difficulty misunderstanding the concept of this particular chapter.
Okay, what you will do is you just go through the basic NCERT or Allen module of chemical bonding. Like you should know what is ionic bond, covalent bond, coordinate bond. Like what are those bonds? You just go through that once, and if you have any doubts, you ask me.
Yes.
Okay. So
Yes.
then whatever the doubts you have here, whatever we are discussing in the coordination compounds or complex compounds, it relates, it's the application of chemical bonding, right? So
Yes.
read that bonding once. If you have any doubts, you approach to me. And whatever I am discussing in coordination compounds is from the basics only. Okay, from the basics of complex compounds. But for
Yes.
that, you have some idea. You have to work on chemical bonding concepts for some time. If you have any doubts, you ask me, I'll clear them so that you can understand these concepts very well. Okay?
Okay, sir. Thank you, sir.
Thank you.